Okay, so let's now look at a couple of things. This will be a relatively short video because I'll be dealing with one short topic and a one which is a bit longer but still short. So I'll be dealing with this particular topic, heterogeneous equilibria and how the Le Chatelier principle comes into play. Now, if you remember, we talked about the fact that if you have a pure solid or liquid involved in an equilibrium system, then their concentration does not appear in the equilibrium expression, the Kc expression. And we're going to see how that applies as far as Le Chatelier's principle is concerned. Now, what you see here is a diagram which represents what happens to calcium carbonate when it decomposes. So let me write down the equation just to remind you of the reaction that we're talking about here. Where shall I put it? Let me try to squeeze it. Hold on 1 minute. Okay, for some reason oh, okay. So I'm going to put it up here. So it's CaCO3 solid to form CaO solid plus CO2, which is a gas, all right? So remember we said that in this particular case, the Kc or Kp, depending on which you're using, let me use Kp. Kp would be simply be equal to the concentration or the pressure, I should say, of CO2, all right? And that's because calcium oxide and calcium carbonate are both solids. Now, the implication of this is that whenever you change the amount of either the calcium carbonate or the calcium oxide, it will basically have no change on the amount of gas that is present as far as carbon dioxide is concerned. So as you can see here, we start out with the calcium carbonate here initially, and then some of it reacts to form carbon dioxide, and you have some calcium oxide left behind here mixed with the calcium carbonate. And if you were to add any calcium oxide to it, the pressure of carbon dioxide will remain unchanged, and the same will be true if you add any calcium carbonate to it. And that's because the concentrations of these substances are not changing. Even though you add more of each of them, the concentration does not change, and therefore it does not affect the equilibrium position, all right? So that's what happens in a heterogeneous equilibrium situation. Okay, and that's all I'm going to say about that, because the next topic I'm going to talk about now has to do with how pressure changes affect the equilibrium position when you're dealing with a system that is in equilibrium and that is totally gaseous, all right? So, if you have a gaseous reaction where there are no solids, no liquids, no solutions, that's what we're talking about, a totally gaseous system, right? So how does Le Chatelier's principle applies? Now remember what Le Chatelier's principle says. Le Chatelier's principle says that if you add a stress to the system in any part which is already at equilibrium, then the system will respond so as to relieve that stress, right? So as stated here, when the pressure of one gas is increased in a system at equilibrium, that corresponds to an increase in the concentration of that gas. And therefore, the equilibrium position will shift so as to relieve that pressure. All right, so basically what we're saying here is that if you were to increase the pressure of a gas in a total gaseous system, then the system will respond by shifting the equilibrium position so as to reduce the pressure, which is tantamount to reducing the concentration, right? Now that's what happens when you change the pressure of one component in the system, all right? Now, what if you change the pressure of the entire system? So imagine, if you will, an entire system at equilibrium where all the components are gases. How will the system respond when you change the total pressure of the equilibrium system? Well, according to this statement right here, this predicts what will happen when the external pressure is increased, right? Or correspondingly, if the volume is reduced, which is the same thing, basically, then the equilibrium will shift in the direction producing a smaller number of moles of gases. So therefore, what you have to do is look at the stereochemistry of the reaction in order to make a prediction as to how the system will respond when you increase the pressure. Then we say further that when the external pressure is decreased, or if the system volume is increasing, then the equilibrium position will shift in the direction favoring the formation of a larger number of moles of molecule of gas. I'm sorry, right? So basically, this is in line with what Le Chatelier principle would apply or would predict. The principle says that whatever you do to the system to disturb the equilibrium, the system will do the opposite to relieve the stress that you impose on the system. So if you increase the total pressure, the system will shift to decrease the total pressure. If you decrease the total pressure, the system will shift in order to increase the total pressure. So that's basically what happens in a totally gaseous system. Now, what happens? Let's consider this possibility. Let's say if there's no change in the number of moles of gas in a reaction, right? For example, this reaction right here, right? The reaction between H2 and I2 to give 2HI. So if you look at this here, you have a total of 2 moles of gases on the left side, 2 moles of gases on the right side. Well, according to Le Chatelier's principle, nothing will happen. There'll be no change in the number of moles of gases in the reaction, right? And that's because there's no way that the system can relieve the pressure if you increase it, or if you decrease the pressure, there's no way the system can increase it because you have equal moles of gases on both sides. So therefore, when you have such systems, there'll be no effect on the equilibrium position if you either increase or decrease the total pressure. All right. So this is just demonstrating what we just discussed here. Now, this is dealing with the reaction between, well, not between, but the reaction of N2O4 gas to form NO2. And there are 2 moles of that, right? So as you can see, it's a total gaseous system. This is a gas here. So this is a gas, this is a gas. So we can look at discussing what happens when we change the total pressure. Now, according to Le Chatelier's principle, let me just make a note here. If we, let's say, well, let me go with the diagram here. Let me get to my pointer. So you start off here with the gas here trapped in this vessel. The pressure of the total pressure is 1 atmosphere, right? All we have here is N2O4 molecules. So when we reduce the pressure, then the system will try to, I'm sorry, when we increase the pressure from 1 atmosphere to 2 atmospheres, the system will try to relieve the pressure. Now, how will the system relieve the pressure? Well, in this case here, we have, let me use my pen here. In this case here, we have 2 moles of gases. I'm sorry, we have 1 mole of gas on the left side, and we have 2 moles of gas, right? So basically, what will happen is that when the pressure increases, so when the pressure increases, the system will try to reduce the pressure. So system will reduce pressure. And therefore, what will happen is that there will be a shift in this equilibrium position from the left side, from the right side to the left side, because you're going from 2 moles to 1 moles. So as that shift occurs, you're reducing the number of molecules of gas, and therefore what will happen is that the pressure of the N2O4 will increase, and the pressure of the NO2 will decrease, all right? And that is what you're going to see here as you go from let me go back to my pointer here. As you go from here to here, ultimately ending up here in this case, where basically you're increasing the number of molecules of N2O4, which would result in a reduced pressure. So here we have actually a mixture of NO2 and N2O4. I think I mistakenly said that this was only N2O4. Here we have actually a mixture of N2O4 and NO2, and therefore when you increase the pressure, right, you're favoring the formation of N2O4 when two of these molecules will come together to form N2O4, and therefore as a result, the pressure will reduce in opposite to what was imposed, which was a pressure increase to begin with. All right. So that's basically an illustration of how Le Chatelier's principle is applied to gaseous systems when the pressure of the total system is changed. You can make such predictions when it comes to that kind of situation. Okay. So we're going to stop here. The next thing we're going to talk about is how temperature changes and catalysts affect the equilibrium position. Until next time.